Here we go. Okay. All right. We will give attendees a minute or two to filter in. Hi, everyone joining us. Thank you. We're going to give it just a minute for everyone to join us, and then we'll begin. Okay, it's 6:30, so in the interest of time, we'll go ahead and kick it off. Welcome everyone this morning, afternoon, evening, wherever you're joining us from, for this webinar presented by the Global Power System Transformation Consortium. My name is Isabel McCann. I am the communications lead for the GPsT, as we like to call it. I will be the technical coordinator today, so I'm just going to take a moment to welcome you all to this webinar, Power System Oscillation Source Analysis using OSLp tool. And I'm just going to take 1 minute to go through a few Zoom housekeeping items and also just sort of instructions for how you can engage today. We do want this to be an interactive webinar, and we have allocated some time towards the end for question and answer. So just a few things to cover. The webinar is being recorded and will be shared with you all as attendees in an email tomorrow, or just as soon as we can get the video rendered and posted on YouTube. So the video is being recorded. That's usually the most common question we get. It's being recorded. We'll share the deck. We'll share the recording with you all. You all are automatically muted upon joining and throughout the webinar to ensure that there's no distractions or noises that pop up and derail the presentations. Please use the chat feature to add any comments. We'd also love if you guys want to introduce yourself via chat. That's great. We'd love to know who's with us this morning. And then there is a specific Q&A function. If you hover over your Zoom toolbar, you'll see that there is a Q&A function. That is the best tool to actually submit questions that you'd like our panelists to address. So that Q&A function helps us keep the questions a little more organized than the chat. So if you have commentary or just something that you want to add or introduce yourself, put that in the chat. Put your questions that you'd like our panelists to actually address or answer for you in the Q&A. Finally, if you have technical issues, use the chat feature, and you can message myself, Isabel McCann, or also Holly Darrow. There is a drop down that you can use. And oh, I see someone mentioned the chat feature is disabled. I'll make sure to enable it. Sorry about that. But you can use the chat to, thank you, Holly, to message myself or Holly. Finally, you can adjust your audio through the audio settings. If you're having issues, you can also dial in and listen by phone. You can find the dial-in information in the registration email that you received from Zoom. So in that, you'll find any phone numbers that you can use to dial in. And then finally, we would love if you all took the short survey that will launch at the end of the webinar. So once we conclude and shut down the webinar, it's going to automatically surface onto your screen, your device screen. That webinar is really helpful for us to understand the impact of these educational events to improve your webinar experience, and also just help us kind of understand new topics, gain support to host future webinars. So with all that said, I will hand it off today to our first speaker, Mohit Joshi. He is an energy systems modeler and analyst at the National Renewable Energy Laboratory, and he also works and is involved with the Global Power System Transformation Consortium. So with that being said, Mohit, I will hand it off. Thank you.
Thanks, Isabel. Hello, everyone. My name is Mohit Joshi, and as Isabel mentioned, I'm an analyst at the National Renewable Energy Lab. And I also welcome you all to this webinar on power system oscillation analysis using OSLp tool organized by NREL and GPsT and with support from POSOCO, the National Power System Operator of India. Just to give you a brief perspective of this webinar, oscillations are very inherent to the power system and pose system threat if not managed properly. So the speed at which these oscillations need to be detected and the source to be analyzed is very important. with support from NREL through GPsT and ISO New England, who has developed this OSLp tool. The Southern Regional Load Dispatch Center of India recently implemented the OSLp tool. This webinar will showcase this OSLp tool for oscillation analysis and also experience of POSOCO in using this tool. Today, we have with us three presenters, Dr. Wang, who will talk about the OSLp tool theory and also the dissipation energy method, which is used in this OSLp tool. He's an assistant professor of electrical and computer engineering at the University of Texas at San Antonio. He's a senior IEEE member. He holds a PhD degree from the University of Tennessee in electrical engineering. In the past, he has worked as an intern, postdoc, and engineer at ISO New England, Texas A&M University, and National Renewable Energy Lab. His research interests include power system dynamics, stability, and control, considering high penetration of renewable energy resources. He has also contributed towards development of this OSLp tool while he was working at the ISO New England, and also provided technical assistance to POSOCO when he was working at NREL. So welcome, Ben, to this webinar. Next, we have Abishek, who is the Deputy Manager at the Southern Regional Load Dispatch Center, POSOCO. He holds a MTech degree in Power System from IIT Bombay. His work area includes system studies, state estimations, SCADA automation, unit commitment, and PMU analytics. Welcome, Abishek. The third speaker that we have today is MVD Raghava, who is Assistant Manager in IT Department at SRLDC POSOCO. He completed his bachelor's in computer science at Shri University in 2018. He has been working in POSOCO to develop in-house IT applications and has extensive experience in developing web applications using Django framework and also doing data science and automation using Python. So welcome, Raghava. Before handing over to the presenters, I will just give you all an overview of the G-PST Consortium. It's a consortium of different system operators around the world and also leading technical institutions. As you mentioned here, it's a consortium of various system operators from, sorry, can you just go back to the previous slide? It's a consortium which is represented by various system operators like National Grid, AMO, ERCOT, California ISO, and also leading technical institutions like NREL, IEEE, ASIC, and all of them which are mentioned in this slide. Next slide. So as I mentioned, it's a consortium of system operators and leading technical institutions. It has a very narrow focus. It focuses on the problem and challenges faced by the system operators, so trying to help them in moving towards energy transition. And then the founding system operators provide guidance to this consortium. Then there is a GPsT core team technical institutes, which are leading various research efforts in collaboration with the founding system operators. And also there are emerging economy system operators like Indonesia, Ukraine, Vietnam, India, South Africa, Tanzania, Morocco, Peru, Colombia, and others who are part of this consortium and then are taking benefits from the wisdom and expertise of this consortium. There are 5 pillars in this whole consortium where we are providing support to the system operators. The first pillar is system operator research and peer learning, system operator technical assistance, workforce development, localized technology adoption support, and open tools and data. And then this specific webinar is one of the showcase of the open tools where we have supported POSOCO to implement such a tool in the control center. Next slide. We provide support to the system operators in a number of ways. So it could be a peer learning with other system operators like National Grid, Cal ISO, and others. So we also provide them technical assistance and training through the technical institutions which are part of this consortium. We also offer internship and fellowship programs, embedded expert assistance. We also focus on learning on research innovation and also trying to conduct joint studies with various system operators and technical institutions. So I'll stop here and then hand it over to Wang for the first presentation on OSLp tool. So over to you, Wang.
Thank you, Mohit. Let me share my screen real quick. Just want to make sure, can you see my screen?
Yes, we're seeing presenter view. There we go. Perfect.
Okay, cool. Yeah, thank you. Thanks, everyone. Thanks, Mohit, for the introduction, and thanks, Unreal and GPsT for the invite. It's my honor to give a talk here. In the next 15 minutes, I will introduce the dissipating energy flow method for locating the source of oscillation. So DEF here is the same as OSLp for this talk, so they are used interchangeably. So in this introduction, I'm going to cover why we need to locate the source of oscillation and how DEF works and how effective it is. So power system oscillations represent a marginal state between stable and unstable states of the system. For the traditional power system dominated by synchronous machines, we always observe like 0.1 to 3 Hz oscillations. They are electromechanical oscillations. And for modern and future inverter-based resources dominated power systems, we will be able to see the oscillations in a wider frequency band, ranging from 0.2 Hz, like the 0.29 Hz oscillation observed by Tennessee Valley Authority last year, and the 8 Hz oscillation observed by National Grid ESO last August, and also a 20 Hz oscillation observed by Kauai power system operator in Hawaii Island. And there could be also hundreds of Hertz oscillations originated from HVDC controls. Those are all oscillations that may appear in low inertial power grid, and that'll be an issue for future power systems. These oscillations are mostly benign symptoms, but some of them may cause damages to generation and transmission assets, and they may even kill people. So we need to manage these oscillations before catastrophic consequences happen. So if we look at the existing research, so most of them are focusing on detection and monitoring. So basically, they can help check the existence of the oscillation or provide a good characterization of the oscillations. For example, to find their amplitude, frequency, damping ratio, and even mode shape. So this can help us to establish a better understanding of what's happening, but they may not be able to help us about what to do with the oscillation. How can we mitigate them? So in the past decade, there's a research topic on oscillation source location, which is to find the destabilizing components in the system. And that's what we call oscillation source. So knowing oscillation source in the system when oscillation happens, that will provide very clear and actionable information for system operator. So that would be helpful to design mitigation strategies. So in the past, we did 2 reviews of the existing oscillation source location methods. One was done in 2015. We summarized all the popular methods, if not all, in the right table here. I'm not going to dive into those methods, but interested audience, I refer to the 2 references listed below for more details. So the second review we did like 2 months ago summarized all the new development, either the improvement of old algorithms and the development of new methods. So 7 years ago, we tested a few selected promising methods for online application. We identified one of them, which is the energy method, to be most effective, and I'm going to talk about that very shortly. And for those new advancements happened in the past 7 years, we are not quite sure how effective they are. So last year, we organized an international contest to find out the answer. We'll also briefly talk about that later. So first, the energy method we picked for an online application. So basically, the energy method was originally proposed by a group of researchers from Tsinghua University in China. We added some data processing procedures and also modified the formula to better handle the real-world measurement data. And then we name it dissipating energy flow method, or DEF in short. So the DEF calculation requires 4 quantities that are measured by phasor measurement unit, including voltage phasors, current phasors, but eventually the direct input to DEF method is PQV theta, active reactive power on the line, voltage magnitude, and the phase at the bus. So the voltage angle can be replaced by the voltage bus frequency. So what's the meaning of DEF? So similar to regular power flow, which is defined on 60 or 50 Hertz, the dissipating energy flow is the transient energy or transient power flow defined at the oscillation frequency. We call it transient because if the system is under steady state, the dissipating energy flow is 0. If you can see it here, it's 0. But if the system is experiencing oscillations or transient, the dissipating energy is not 0. And the sign of the dissipating energy can help tell where is the energy is produced and where is it absorbed in the system. So after we calculate the dissipating energy flow from the measurement data, we can put an arrow on the one-line diagram of the system, and that can help us trace down the oscillation source. So here's the illustration of DEF method for oscillation source location using 2 real events happened in ISO New England area. The left one was an event in 2013. So the DEF produced by a generator, which is represented by a very big arrow here, is spread into the system over the network. So we can easily see that the oscillation is originated from this generator here within ISO New England area. The second event on the right-hand side was an event in 2016. When we monitor the timelines between New York ISO and ISO New England, we can easily see that the dissipating energy flow is flowing from the New York ISO area and into the ISO New England area. So with that, we can conclude that the destabilizing components in the system for this oscillation is located outside ISO New England area. It could be within the New York ISO area, or it could be other areas behind New York ISO. So if you are the operator of ISO New England, you can clearly know that whether you need to take control actions to mitigate the oscillation in the 2 scenarios. For the left one, you need to figure out the issue. For the right one, that's not your problem. You can inform New York ISO area or other areas to let them know they have a problem. So here's the implementation of the oscillation management at ISO New England. So the DEF, which is named as OSLp, has been integrated to the control room application at ISO New England since 2017, and it's been working 24/7. So during the 2 years between 2017 to 2019, there had been like 1,200 plus events captured and processed by this tool. And this tool showed very high reliability. For any event that can be verified, this tool can give you the right result. And the right-hand side gives you a picture showing what is produced by this application. So basically, an email will be automatically generated, including all the parameters of the oscillation and also where is a source. So this tool has been fully automated, working continuously in the background. So that's very convenient. Next, I'm going to quickly talk about the oscillation source location contest we organized last year. Basically, it was co-hosted by IEEE and NASP, and our goal is to find out the most effective tool for oscillation source location in today's market. So anyone is welcome to, well, everyone was welcome to participate except for the committee members, because we were designing the problem, so we were not allowed to participate by ourselves. So basically, we designed 13 very challenging and rarely seen, but they are realistic looking, simulated oscillation events. 60 teams from all over the world sign up, and 21 of them provided their solution to us. So here's the summary of the result they submitted. Basically, all the methods they adopted can be classified into 4 categories. The first one is the energy method. And if you look at the result, you can see that the teams using energy method or DEF method tend to have higher scores. And there are 2 things I want to highlight here. The first one is the implementation matters. So although they all use DEF method, but some of them, if implemented properly, may have a higher score. If they don't implement the DEF method properly, they can get a misleading result. So another thing I want to highlight is machine learning or artificial intelligence-based method. So if you, which is the third method here. So if you only rely on artificial intelligence, it seems that it cannot work very well. But if you combine machine learning and artificial intelligence with some existing method, for example, the DEF method, that can help to achieve a better accuracy in terms of oscillation source location. So next I want to quickly mention where to get the DEF tool. So the first source is the OSLp software, which is version 1.3 provided by ISO in England. It's free of charge, but you have to request that from the link here. Just send an email and put a few words to justify your need, and then they will share the source code with you. So every single details in the code will be open to the user. So you can modify that based on your need. The second place is the DSA tools by PowerTech Labs. In its output analysis module, there is a built-in DEF tool. So if you want to deal with some simulated cases for planning purpose, you can use the DEF there as well. So here I also want to quickly mention the use of the OSLp software version 1.3. So that's the version we actually ISO New England currently shares with everyone. So Unreal has a copy. We used it to analyze the 20 Hz oscillation event happened in Kauai Island in Hawaii. So, and also we share this tool with Southwest Power Pool in the US. And in this summer, we were glad to share the tool with POSOCO in India, and they will share their experience with the tool very shortly. And I think only recently we shared this tool with National Grid ESO in UK, and they were using this tool for investigating the 8 Hz oscillation happened last year. So we are happy that our tool is able to help other system operators to deal with oscillation events. So if any institution is interested in getting the tool, so feel free to request it by this link here. So currently, as I mentioned, the one we're sharing is version 1.3, which contains several very useful techniques there. And we are constantly improving the tool by adding new features based on our improved understanding of the tool itself and based on our improved knowledge of the oscillation event. So to wrap up, DEF is an online application for locating the destabilizing components in the system that drive the system to oscillate. The DEF tool is not perfect in theory, but is currently among the best tools for handling oscillation events. So we need to improve it. Also, we need new tools or better tools for more effective management of oscillations. And another thing is how effective the DEF tool will be for inverter-based resources dominated oscillations. That is still an open question, and we need more investigations on that. And this slide listed the references for interested audience. And with that, I will turn it back to Mohit. Thank you.
Thanks, Ben. Thanks, Ben. This has really been insightful to understand the effectiveness of the DEF method. I request participants to use the chat box to send their questions, which we will be taking after the next presentation. So for the next presentation, we have Abishek and Raghava from SRLDC's POSOCO. They'll be talking about the experience of implementing this tool and also the dashboard that they have created for this specific tool. So I hand it over to Abishek.
Thank you, Mohit. I'll just share my screen. So thank you, Ben, for the presentation, for setting up the context. Now the outline of our presentation. First, we will have an introduction, an overview of the Southern Regional Grid and the OSLp journey which we have had so far. Then we will give an overview of the DEF method which we have implemented. Then finally, we will look at some case studies. After that, we will see what challenges we faced while we were practically implementing OSLp in real time. Then we will have a demo of the dashboard which has been developed in-house. Coming to the overview of the Southern Regional Grid, the Indian grid has 5 regions, and the Southern region, this tool has been deployed. Some highlights of the Southern region is we have met a peak demand of around 61 gigawatt with a maximum daily energy consumption of 1200 million units, a maximum solar energy generation of 95 million units. The installed capacity is around 120 gigawatt. The fuel mix is mainly dominated by thermal and renewables, followed by hydro and other sources. The transmission network has around more than 50,000 circuit kilometers of EHV lines. Now coming to the major costs of oscillations which we see in Southern region is, the first major cost is when a generating station loses a major set of evacuating lines and the evacuation of power happens through a very weak network. In that case, we see a lot of oscillations. And another case is when the generator control system, especially the turbine governance system, maloperates. So these are the two main causes of triggering oscillations that we have seen. And we have around 315 PMUs present across 95 substations. So on a whole, we have more than 600 signals to be analyzed. Now coming to the OSLp journey so far. First, NREL and ISO New England provided the OSLp source code in MATLAB. We are very thankful to them. This MATLAB program was converted to Python because many of the in-house applications already present were based on Python. So converting this to Python helped for easy integration to other modules. And this Python program was first tested and validated using offline PMU data. Now then parallel processing techniques were used to improve its speed because we have around 600 signals, and this algorithm, each signal is a 5-minute duration signal, and with a PMU sampling rate of 25 Hertz, we have more than 4 million samples to be analyzed. So we had to use parallel processing techniques to speed it up. And finally, after parallel processing was used, the entire algorithm takes around 1.5 minutes to run. After this, it was deployed in real time. Now, this is not run always. We have a trigger for this. We already have an event detection engine which runs on real time, and that is based on Z-score. So whenever the event detection engine detects an event, at that time, the OSLp is also triggered, and it checks for whether there are any oscillation or not. Then finally, the real-time results are viewed in a dashboard so that the operator can analyze it easily. Then we have also added matrix pencil method to supplement the DEF method to give mode damping and mode shape to see which are the coherent group of generators, which is swinging against what. So that we can use matrix pencil for that. Now coming to the overview of the DEF method, which is the core algorithm, as Ben has explained. First step is data cleaning, where the outliers and stalled signals are removed and they're interpolated. Next is the identification of the dominant mode of frequency using FFT. Once the dominant mode is identified, the real power signals for all the branches is filtered for the dominant mode. And the signal which has highest magnitude for the dominant mode is designated as the study line. And the study line has the entire 5-minute data. That 5 minute is not necessarily that the entire 5 minute is having the oscillation. So from that 5 minute, we'll have to find the exact time window where the oscillation is predominant, which is called as a study window. The study window is found by running a moving FFT window, and we will see where the FFT magnitude is more than a threshold. And those time samples will be considered as the study window. And after the study window is found, all the signals will be sliced for the study window. So the 5-minute initial window will become, say, the 20-second time window. If this study window is 20 seconds. And once the study window is found, all the branch power flows, we will find the dissipating energy. That will be computed. And depending on the direction, it will be mapped onto the geomap so that we will get a clear picture of where the source of oscillation is. Now coming to the case studies, we have 3 case studies. First case study is large amplitude oscillations inside the region, how OSLp performs for that. The next case study is small amplitude oscillations, again inside the region. We are checking the performance. And finally, the third case study is small amplitude oscillations, but outside the region. Now, this case study, this is a 1 gigawatt hydro complex, which evacuates power through the 220 kV network. And we can see substations Sirsi and Shiralkoppa, they are radial substations. Since they are radial, the loading of these lines is independent of the amount of power generated. So this loading is very less, it's around 10-20 megawatt only. So the majority of the power generated by this plant is evacuated through the 3 lines to Shimoga. These 3 lines is a major corridor, and another major corridor is the 3 lines to Talaguppa. And after that, it gets stepped up to 400 kV and it is evacuated through a single long 284 kilometer line to Hassan. So at April 27th, we had an incident, and just before the incident, this is the SCADA snapshot, where we have the Sharavati generating plant generating around 750 megawatt it generates, and majority of power goes through Shimoga, around 450 megawatt goes through the 3 lines, and another 100 megawatt goes through another 220 kV path, and around 179 megawatt is evacuated to the 400 kV network. And what happened during this time is the bus bar protection operated at Shimoga, tripping all the 220 kV paths. So as you can see here, all these 220 kV paths have gone 0. Even the longer path via Gerasoppa has also gone 0. As a result, the entire generation comes to Talaguppa, and entire generation is evacuated through a single long 400 kV line. You can see here the flow has become 757 as captured in the SCADA. Now, large amount of generation evacuated through a very weak network is the perfect recipe for having oscillations. And that is what we saw. And the oscillations lasted for around 30 to 40 seconds. And the plant operator, Somoto, started reducing the generation. So he reduced the generation from 750 to 250. So there's a 500 megawatt reduction. And after the reduction, the generation is 250 and the entire power is evacuated through the 400 kV line is only 240. So it is comfortable and the oscillations die out. Now the analysis for this event is as follows. First, the FFT is computed and the dominant mode turns out to be 0.74 Hertz. And then the study line, that is the line which is having maximum amplitude of this 0.74 Hertz was found out. And that was Hassan Talaguppa. This was expected as this is the line which has a PMU and is closest to the Sharavati station. And as you can see here, the peak to peak amplitude is as high as 400 megawatt. The peak to peak amplitude of oscillations is 400 megawatt. So very high amplitude oscillations. And the time window, the study window is also correctly identified by the method as shown in the red line. Around 30 to 40 seconds is the length of the study window. Now, after the study window is identified, all the signals are sliced for the study window, and then the dissipating energy is computed for each branch, each of the 600 branches. And the top 5 highest dissipating energy branches is plotted. As you can see, the one with the highest slope is the closest to the source of oscillation. So the highest slope is the Hassan to Talaguppa line having a negative slope. The slope is negative because dissipating energy is flowing into Hassan bus from Talaguppa bus. The PMU is at Hassan. That's why it is negative in sign. This is already explained by Ben in his presentation. And then the next dominant one is again Mysore Hassan at Mysore end, which is negative. So the dissipating energy flows from Hassan to Mysore. Now these top 5 arrows are mapped onto the map. And from here, from the map, we can very clearly see that the flow is into Hassan, and from Hassan, it's all outgoing. So Hassan PMU is the closest PMU to the source of oscillation, and the source is correctly identified as Hassan. Now coming to the next case study, where we have small amplitude oscillations in southern region. Here one hydro unit, a very small hydro unit, which is connected at the 110 kV network. This is actually connected in the 110 kV network, and that had tripped, and that triggered small amplitude oscillations. This box out here basically shows there is network in between. It is not directly connected to Kalamassery bus where there is a PMU available. So this is the network. And the analysis for this event is as follows. The FFT was 1.15 Hertz, higher than last time, as it is a local mode oscillation. And the study line turned out to be Udumalpet-Palakkad line, which is not the closest to the source, but it is not closest, slightly far off. But this is the happened to be a study line, and the peak-to-peak oscillation amplitude is around 20 megawatt, so very less when compared to case 1. But here the oscillation sustained for around 100 seconds, and then it suddenly reduced in amplitude. Again, the DEF was plotted, but here DEF wise, if you see, the source is correctly identified as Kalamassery Kochi. So here the interesting thing is that the one with the highest D is not necessarily the study line. The study line need not be the line with the highest dissipating energy. Always the highest slope of dissipating energy is associated with the source of oscillation. So it is correctly identified. The source is Kalamassery to Kochi. So Kalamassery PMU is the PMU closest to the source of oscillation, even though the Udumalpet-Palakkad line has the highest magnitude of the 1.15 Hertz mode. Now coming to the final case study, where small amplitude oscillations were observed on the interregional lines, and the southern region is connected to the rest of the Indian grid through these AC interconnections as shown, and PMUs are available as shown in the diagram. Now small oscillations, amplitude oscillations was observed in the interregional lines, and the FFT analysis gave the mode as 0.63. 0.63 is the dominant mode, which we are seeing here. And then the study line turned out to be Raichur-Sholapur line, which is one of the interregional lines connecting western region and southern region. And here another interesting thing, there's 2 sets of oscillations, 2 regions where the FFT magnitude is more than the threshold, but the study period, study window is the longest such window. So the second window is chosen as the study window. And again, the DEF for all the lines are plotted. And here we can clearly see that the Sholapur to Raichur, that one has the highest slope and is positive direction in Sholapur, which means energy flows from Sholapur to Raichur. And similarly, for all the interregional lines, we see the flow is from western region to southern region, indicating that the source of oscillation is somewhere in the western region. Now, next part is relates to the practical implementation of OSLp, which will be handled by my colleague Raghava.
Hi, good morning everyone, and good evening everyone, those who are present, attendees. Now I am walking through the implementation of the OSLp in our SRLDC at POSOCO. First, the MATLAB code that was given by the new SR England was converted into the Python program and tested for the offline data. After testing for the offline data, we want to implement it in the real time. For implementing in the real time, the real challenge is that it has to work for all the 640 megawatt signals around a SR grid in a real time basis. That it has to run very fast. For that, we have used the modern package. It is a basically Python Intels package that used to that helped us to scale up our pandas workflow very efficiently. After doing this, after using this package, we could be able to locate the source of the oscillation within a 1.5 minutes. Then after getting the results from the OSLp engine, we need to store the results. For storing the results, we use the Postgres database. And after storing the results, to visualize the results to the operator, we have used the Grafana dashboard to create to visualize, and e-charts to trend the megawatt flows and whatever, and Conva library to visualize the dissipating energy flow on the geomap. Now we'll go through the workflow of the implementation here. First, the OSLp engine will be triggered by an event detection engine that is developed in-house using JetScore method. Once we get the trigger, we'll extract all the megawatt signals from the GE UART-DSM servers for a 5-minute duration at a data rate of 25 Hertz, which is a very large data. After getting the data, we are cleaning the data to remove all the lines which are out, and then we will perform the time analysis and spike analysis to find out the time at which the oscillation is present. After finding out the time, only for the duration of the time where the oscillation is present, we are extracting all the megawatt signals and positive sequence voltage magnitude signals, which is required to calculation for the DF. Here we are not using for all the 5-minute duration, but we are using only the time that was identified by the OSLp program, so that it will we can run the program very fast. After that, we are calculating the DF for all these lines using these parameters. Once the DF is calculated, we are identifying the top 5 DF lines where the energy is flowing maximum. For only those 5 DF lines, we are performing the matrix pencil analysis to get the dominant modes and corresponding damping ratios. Once these results are got, we are storing those results into the database and visualizing in the dashboard. Now we will go very quickly walk through the dashboard. This is the dashboard that was prepared. These panels represents the mode of the frequency of the oscillation mode and corresponding damping and the oscillation start time that was given by the program. And these panels gives the power spectral density of the signals and corresponding mode shift for the top 5 DF lines. And sorry for this. This is a network diagram where giving the dissipating energy flows of calculating DE flows. Here it shows that there is and pinpointing to the oscillation source location that will give an immediate attention to the real-time system operator. Here you can see that the energy is flowing into the Hasan bus, and from the Hasan bus, the energy is flowing outside. So it is the source. And then these panels represents the time analysis output from the OSLp program. This is the maximum line power where the magnitude of the oscillation is very high. And this is for the 5-minute duration, and the OSLp found out that this is the time where the oscillation is present. And this panel represents the FFT scans, giving the magnitude for each scan. These panels represents the filtered mode of the raw power of the dominant mode frequency, and correspond. This one gives the top 5 DF lines, DF plots. This is the eigenvalue analysis that we performed on the top 5 DF lines megawatt flow. Here, these dots represents the real part of the roots for plotted corresponding to the frequencies. And the 3 lines here represents to the damping ratios. The red line represents the 3% damping, green 15%, and middle orange represents the 10% damping ratios. Right side to these 0 axis lines are the modes with the negative damping. And these right side panels gives the megawatt flows for all the top 5 DF lines that were identified by the program. And there is a link provided here so that they can the viewers can go to the corresponding dashboards where they can view all the corresponding parameters also, like megawatt, voltages, and all for the given station. Now we can go through the real-time events or a demo of the dashboards in the real time. Here we are seeing the oscillation event that was detected today morning at 8 o'clock. It is an event that was generated by a lower Sileru, that is a hydro generator present. Here you can see the maximum line power magnitude was found at Solapur Raichur, but the oscillation source was identified at KTS lower Sileru by the method. The panels corresponds to what I explained earlier, mode shapes and all. Along with this also spike analysis output was displayed. Along with that matrix pencil analysis which we have done was corresponding mode shapes were displayed for all the frequencies identified with the corresponding damping ratios. These are scaled to the magnitude of the maximum dominant frequency. So here you can find. Thanks for the giving us this opportunity to present. I thank POSOCO, SRLDC, as well as the GPsT for providing us this opportunity. And I hand it over to the Abishek to conclude.
That's it from our side.
Thanks, Abhishek. It was really useful to understand how you have implemented and then also what results you are getting. So thanks so much for that. So we'll now move on to the Q&A session. We have a few questions coming up from the participants. So I'll start those. So I think, Ben, the first question is for you. Like, is this OSLp tool linked to specific PDC, or like, if yes, which one? And then is this tool free and also open source or not? So
no, it's not linked to a specific PDC right now. I mean, it doesn't have to be linked to a PDC. So far at ISO New England, we use the tool in a centralized manner. So we collect all the data and then apply the method to process all the data, so we can have an overall evaluation of the DF throughout the network. Then we can determine where is the source. So that's one way to use it. There is another way to use it, which is to do the calculation at a PDC or even at a PMU, measurement location. So we can, in that application, we cannot find the source. We may not be able to find the source, but we can still conclude whether the monitored location is the source or not. We can conclude that. That's the first part of the question. And is it free?
Yeah.
Yes, it is free of charge. You just need to send an email to justify your need, and then ISO New England will share the tool with you, including all the codes open sourced. So nothing will be in script.
Thanks. So the next question is for Abhishek and Raghava. Like, how long does it take to fetch the 5-minute data from the URT DCM servers, and then and how many PMUs it fetches? So, and then one question from my side, like, how long does it take to process the overall data and then give you the final results?
Like, it is taking around 40 seconds to get the 5 minutes data from the OSLp server. And we are fetching megawatt signals, not PMUs, like for each line megawatt signal for 5-minute duration. It takes around 40 seconds. And after that, we are identifying the time oscillation time. After that, for a very short period of duration, like 20 seconds or that, we are fetching all other parameters like voltage and frequency. For that, it takes around remaining 40 seconds to do the calculation. Overall, it is taking around 1 minute 20 seconds to 1 minute 30 seconds.
Okay, that's good to know. Okay, next question is for Bin. Like, how does the DEF process the PQV and PMU data to return the source location? I think you covered something, but then maybe given like a brief again.
Yeah, I think all the details can be found in the paper we published in 2017, the first paper on DEF. But to briefly, summarize what's happening there, DEF is a numerical integration of the PQV theta, the 4 signals, and no more network parameters will be needed, like the impedance or admittance of the network. We only need the measurement data of the 4 quantities. So what we use are not those direct measurements. We need to pre-processing them. Basically, we need to calculate the deviation value of, regarding the oscillation. So we need to use the deviation value relative to the steady state of the oscillation. So those deviation value will be used for the numerical integration. So you can find the formula in the paper and more explanations there.
Thanks. The next question, I think, is for Abishek and Raghava. Like, someone wanted to understand, like, what do you mean by the localized event in the small oscillation case study?
The localized event is the one which is not observed throughout the grid. If it's an inter-area oscillation, then the observability will be there all throughout. For example, in our Sharavati case, the maximum observability will be maybe 3 or 4 levels beyond that. For the Sharavati event, we may not have any observability in Andhra Pradesh or in the inter-regional lines, and vice versa. So all the 3 case studies which we have shown are all local modes. The frequency is all high, it's all more than 0.5 hertz. Generally, in inter-area mode is around 0.2, it will be very low. So all the case studies which we have shown is all local modes where we are trying to pinpoint the source.
Okay, thanks, Abhishek. Bin, how to proceed further after identifying like generator PMU bus? So maybe the person wanted to ask like what to do next in case they identify the source of oscillation.
Well, that depends on the risk, right? When we see oscillation, that's a risk. It doesn't necessarily means direct damage to your system or to your personnel. So we don't know. So if it's usually if it's small amplitude oscillation, we just leave them there, and at the same time we need to look for the cause and try to mitigate them. But if it's large amplitude oscillations, we probably need to take some immediate actions, like we disconnect the source from the network and then ask the owner of the source to figure out the issue within their control or in their anywhere in their system to fix the problem first before they get back.
Sure. I mean, and then maybe Abhishek, you can also give your input, like what generally do you do when you identify the source of oscillation in real time?
In real time, presently, we don't have we're just using it for offline only. That is, in the sense, it runs real time, but we're not taking any action based on it. Next, what we plan to do is we plan to send a mail to control room saying that there is an oscillation detected and send it to the states. If we find it in, say, Karnataka, we send a mail to Karnataka SLDC. That will be the next step. Before that, we will have to first weed out the spurious oscillations. Presently, what is happening, as and when event is detected, this engine runs and it throws some result. So a lot of results are there. Even today, we may have 20-30 results. But one genuine result today, which we got, was a lower Shiller oscillation at 8 AM today. So in that cases, we'll have to filter it and send a mail to Andhra Pradesh SLDC saying that we observed this and for your necessary action like that. That would be the next step.
Okay. Ben, can this tool be used to assess whether an oscillation originates from the grid or an IBR by using the measurements at the IBR point of interconnection?
Yeah, great question. From the procedures point of view, there's no challenges at all. It's just a signal processing procedure. So, but how effective this tool will be, we don't know. We haven't had any experience with that. So far, we only apply this by myself. I only applied this to the oscillation event. The 20 Hertz oscillation event happened in Kauai Island in Hawaii, which happened last, November 2021. So it's been very helpful. But regarding others event, IBR related events, I don't know. So far, the effectiveness of the tool has been demonstrated for the traditional electromechanical oscillations through, thousands of applications of the tool. So it's been really reliable so far.
Okay, thanks, Ben. Abishek, the next question is for you. Like, what challenges did you face in implementing this OSLP tool? Was it like simple plug and play type, like you got the tool and then integrated in your system, or like did you had any challenges which you overcome and then which other system operators might be able to like get lessons from?
The first step was converting it to Python and validating it properly. So we used to run the MATLAB, and that took some time. And after that, the next challenge was, I think Raghava will explain about the portal, what challenges we faced.
Yeah, implementing in the real time was a challenge because it will not, it is running, it is taking so much time to run in real time for this huge data. To implement in the real time was a challenge. And after that, we are storing the results and making a dashboard was the another step which we have developed. And identifying the corrective thresholds for the frequency filtering and all also was the challenge that we observed using the past data, and we found the correct thresholds and kept for frequency filtering or for finding FFT filtering and all. That was the challenge.
Okay. Ben, what are some of the prerequisites to use or implement this OSLP tool? I mean, you mentioned that we need PMU data. Is there anything else that is required, or like, and then how many PMUs are needed? Like, is there a minimum number of PMUs which will make this tool effective?
Yeah, I would say at the minimum, if you have the PMU measurement from only a single location, you can still apply this method to the few lines that are being monitored, but the conclusion you are making is very limited. You can only conclude what's happening there. So the larger area, being monitored, the more, you can conclude more about the oscillation source. So you can find the more accurate location of the source.
Okay. I'm just going through the list of questions. Another question is for you, Ben. I mean, there are a lot of questions for you because it's on the DEF and tool side. So how effective this tool is in like identifying the inter-area oscillations?
Well, that's a great question. Well, I think we have to clarify that there are mainly only two types of causes for oscillations. One is forced oscillation, which means there is a periodic, external periodic disturbance applied somewhere in the system, driving the entire system to oscillate. So that is called forced oscillation. So DF is very effective in identifying the source of forced oscillations. And the other cause of oscillations is the so-called poorly damped oscillations. Basically, if you linearize the entire power system, you calculate the eigenvalues. And if you find any eigenvalue whose real part is close to 0, but still being active, that is called a poorly damped oscillation. So poorly damped oscillation is a system natural mode. So so far it's very hard to define the oscillation source for natural mode oscillation. So when you are talking about interior oscillation, if it's caused by false oscillation, then DF2 is very effective. But if it's a poorly damped, DF may provide you some results that could point to some equipment that contribute negative damping. But for this part, it's not well verified conclusion. So we still need more efforts to investigate to justify that.
Thanks. I mean, and I'll take only, I think, one or max two questions because we are almost at the time. So I think Abishek and Raghava, maybe you can take the next question, like how small can the selection window be in terms of time? You mentioned about the selection window. So how small that can be if the oscillation only exists for, let's say, 5 seconds? Can we still use this tool? I mean, based on your experience?
Yes, 5 seconds is good enough. It's not, it can be used. There is no issue. The smallest time window is limited by the PMU sampling rate, 25 Hertz. That is the smallest window that can be used. Apart, it will just take, it's a moving window FFT. It will just see where the FFT threshold is more than FFT value is more than the threshold. If it is more, then it will be flagged, and it checks for consecutive scans where it is more. And the longest set of consecutive scans will be the window. So there is no limitation on the size. It is limited by the PMU sampling rate. That is the, so 5 seconds is very comfortable. It can detect. No issue with that.
Thanks, Abhishek. And I think we are close to the time. So I thank all of the participants and also the panelists for making time for this presentation. We really value your time. As mentioned by Isabel earlier, that this presentation and recording will be shared with all of you. There are some upcoming webinars from GPsT. Look out for. The next one is tomorrow, November 17, on learning from Vietnam experience on high fluctuation of variable renewable energy in the grid systems, and a couple of more coming up in December. So please register for those as well. So I thank all of you for the participation today. Looking forward to talk to you again sometime in future. Thanks, everyone.
Thank you, everyone.
Thank you. Thank you all.
Thank you.